so I will try to keep cool, and I'll try to go. I have a lot of slides, but I will just say a few words on each slide. So your coffee will be ready very soon, okay? So don't worry about that. So let me just tell you that we had 4 time slots and 14 talks indeed, but 12 essentially in our field with the calorimetry. And it was divided in some kind of 4 lots of talks. One is about the CPC calorimetry activities in China, and it's very important to see what is going on in China. And one about the higher granularity calorimeters in the world, more especially in Calais. And then one on dual readout calorimetry, and essentially the activities in RD52. And then we invited some people to talk about electronics, etc., which is very important now. I mean, electronics is really becomes the heart of our activities in calorimetries, and we have to take care of that carefully. So let me just a few words. I will just show you slides, but concerning the activities in China, it's important because this is CEPC is, after all, will be built in China, and the activities of the Chinese group is very important to be mentioned and underlined. What I did, okay. So I'm learning. Okay, it's very, I mean, the calorimetry now in China is very active field, really. And it's more on the highly granular calorimeter than on a dual readout. Maybe our colleagues working on readout will not be happy now, but I think it means that in the future there will be more activity. So they should expect that this will be good collaboration in the future. And there is a good collaboration between the Chinese groups and Calais groups. And part of the Chinese groups are now important groups in Calais group. So this is very important. And there is also very interesting R&D with the new prototypes, what I call China-made prototypes. And in the beginning, frankly speaking, I was saying, what is the use to repeat what we did in Calais? But you will see, and I will show you now, that they have new ideas and new demonstrations that are very, very interesting. So it's not just a repetition, it's also a creation, and it's very important. And also there was optimization study for CPC calorimeters, and this is also should be followed carefully. Now, if I repeat this like each time, I will lose time. Okay, so let's start. There was a talk by Minji Dong and about the use of scintillator tungsten as vehicle for CPC. And what I want to mention is that they did some work in order to, you see this is the kind of scintillators. And the idea is you have small pieces rather than to have one tile of 1 square centimeter, to have small tiles, and you have X and Y, and then you can, from this, you can have the resolution you need. But what is interesting, and these are works that was presented, that how to, when you have your style and you put your silicon PM here or here, you will not have the same light yield, and you need the homogeneity. And this was probably proposed by our Japanese colleague, who's very sophisticated models, but what it was proposed here gives you a better homogeneity. This is very nice, okay? So this, I mean, kind of things that contribution is very helpful. And not only about these geometrical things, but also the materials they are using. And several materials were tested, okay? This plastic, video, and this allowed them to go to decide which kind we could be very helpful for the future. And you can see here, and this is very interesting, this is the starting block for this, all the activities, and you see the electronics now is being developed. And also, and this is, I was really astonished and happy to see that, they start to build the first layer of the prototype. But if you look this here, this is a kind of very interesting thing. You see this omega group ASICs, but you see here CEPC. So step by step, we are working together to build the future. And this is very exciting. And this is a message but at the same time, we can get profit of what was done by the Japanese group working in ILC and use the activities in China to combine all of this in order to build the future prototype. Now, then there was a talk by Boxiang Yu about the activities on HCAL, and one of the activities is on the SDI HCAL. Here, the Chinese group, they didn't build, but they participate within CALIS to exploit the data and work together. And you see here, we are working with the Tsinghua group, and we have a common student. I will not go into details about the detector itself. It's not the most important thing here. What is interesting is how to exploit the data and how we collaborate together. And one of the work that was shown is the work of Bing Liu, who is a common student between Lyon and Tsinghua. And he is really doing very nice job. And the idea is to exploit the high granularity detectors, because high granularity, of course, many people say that it's expensive, etc. But also, it's a real treasure, and it's very, very interesting, because you can use the shape of your particles showers in order to discriminate between them. And you can see his work working on the density, the radius, the track multiplicity, which cannot be offered by other solutions. Here, he was able to separate really in a clear way the pion from electrons and from muons. And then, using this separation, he applied the same techniques to estimate the energy. And you see, he confirmed that with other selection, more sophisticated, whatever, he obtained the same linearity and the same resolution. And then he will use this method, this new method that were developed in Tsinghua, in order to estimate the energy. And I'm quite sure we will improve on the resolution using this method, okay? Now, the other activity in HCAL, it's related to using the micropattern gases detector. And there was a development by the Chinese groups to use GEM and also micromegas, but essentially GEM. And they built their own small prototype. Of course, it's not very huge. It's 30 times 30 centimeter detectors. And here also the collaboration with this Omega group and the ILC activities group, you can see they were able to build their first prototype, and they also get a profit of the techniques developed by CERN. I mean, the stretching that now is applied for CMS, whatever. So they did the work, and they obtained very nice results. If you can look at the efficiency, for instance, you can see that the efficiency is really very high, 95%, but the multiplicity, and the multiplicity is lower than the RPC, for instance. It could be interesting if you want to go really more granular to use GEM rather than to use RPC, even if it's more expensive. But it depends. I mean, each item has its own price. Now, the other option that the groups are developing right now is also to apply to use the analog hadronic calorimeters. And I think they obtained a budget for this. They will build a prototype. And Boxiang Yu showed us the activities. And here also you see that how you put your silicon PM in dimples here and to read the tiles of 3 times 3 centimeter, like for ILC project, okay? But then they started to do their own development. And also here you can see they started to do, and they tested several kinds of silicon PM. And this is interesting. And I will let you go. But before to show you some results concerning the silicon PM, let me tell you that many activities to qualify this structure, what is the best, and about the uniformity. And this confirms the result obtained by other groups, for instance, okay, the DAISY group. And this is interesting. And now just one word to tell you that we mutually get profit. I mean, either for ILC or CMS or FC or CPC, whatever, when we have groups working on this kind of nice devices, which is the silicon PM. And you see that there's a development by Chinese group, which is the normal University of Beijing, and they got a really very nice result with this one. And you can see that they have this photo detection efficiency, which is 39%, okay, with a low noise. So it's interesting. Of course, probably this should be compared with the Hamamatsu product, etc. But we are on the right way to achieve this challenging thing. Then Hang Zhao showed us the simulation on CPC, and you can see this is the whole chain was developed. Though you can do everything you want to do, and I think this is nice effort. Of course, in the beginning, it was in collaboration with the ILC staff, and then step by step, this became something that the groups, the Chinese groups and the CPC groups are able to perform. And he showed us some studies concerning what is the best geometry, what is the best size of the pixels you need. This is a very interesting studies within the concept of CPC to decide should we have 1 centimeter or 0.5 centimeter, whatever. And the result could be shown here. And you see that the decision is to go for, depends on what you want about your efficiency, but also about the jet resolution you obtain after. So this is ongoing. And I mean, there was a question about what is it, how to take the decision. This kind of studies are very important to take the decision, not only for the technology, but also for the structure of your technology. As I said, this is a study will allow you also to decide how many layers you need for your eCal, for instance, and what is you need really 30 layers or 20 layers. But if you play with the thickness of silicon, maybe you can compensate. And please keep in mind that is very expensive, okay? And keep in mind that, for instance, for ILC, it's about 100 million channels. But in ILC, you have power pulsing. But here, you don't have it, really. So reducing the number of channels without impacting the physics is very, very important issue. And this should be done carefully in CPC. Then there was also a study concerning the HCAL, and Bingyu presented us the fact that for ILC, there was 48 layers proposed for HCAL, but it's not needed for CPC. 40 layers probably are enough. And it's also the same. You reduce the cost and the power consumption, okay? So this is ongoing. And 40 layers now is considered as a good choice. Now, the second part is about dual readout. And you remember that there is this area concept proposed. And the heart of this concept is the dual readout calorimetry. And John Hauptmann showed us and reminded us what is the importance of this concept. I mean, this is very interesting because, you know, this hadronic shower with the fluctuation, it's not an easy task, and it's one of the problems. And maybe the dual readout could be the solution, because by reading out with the two kinds of scintillators, two kinds of fibers, one is scintillating fibers and the other one Cherenkov fibers, with different sensitivities to the hadronic part of the shower, then probably you have two equations with two unknown things, and from this you can really solve and find the energy. And it's shown here because you can see that you have something which is the correlation between the two of them will allow you to measure the energy. This is a very nice idea, by the way. Of course, myself, for the application, maybe I don't believe, but the idea is excellent. So if people are able to realize this idea, I think it will be a tremendous thing. And people are doing their best to do that, and I will show you. So John showed us some, I think this simulation tell us that if the difference, even if you have pion and proton, and with the other calorimeters you may have some differences, with this concept, you have no difference whatsoever between the two of them. And this is an excellent thing. This is really features that should be put forward. And he also showed us from this study that separating electron from pion within this detector is an easy task. I mean, you see this several features, and if you take only one of them, maybe you are able to separate, but taking all of them, you see that this separation is really wonderful. And not only for the pion electron, which is for me is the most important, but also you can separate easily between pion and muon. Then Ronaldo showed us the activities on the test beam, because several prototypes were built, because you know it's a very sophisticated concept and you need to show people that it works. And this is the history starting 2003, 2012. And you can see that not only the kind of absorber is changed, the calibers of these fibers, but also the number of photodetectors that are used to read that. And what is interesting that for the recent model, our colleagues working on dual readout, they also found that it will be very interesting if you read fiber by fiber. Why? Because in addition to all these nice features, you will win on granularity. And then you go to, say, to discuss with colleagues people saying, listen, we have both what you have in. Huh? But this is a very nice discussion to improve both of us to work together and to improve. And this is the description of this prototype, okay? And I will not go in details, but the idea is to have the readout of the fibers, one level for the scintillator fibers and one for the Cherenkov fibers in order to reduce the crosstalk, okay? Let me remind you that the yield, the photon yield for the scintillators is, I think, 50 times higher than for the Cherenkov, so you have to be really careful about that. And he showed us some interesting results, okay, for the Cherenkov, where you need to have this high efficiency, but for the scintillators, it's too huge, so you need not. And then you combine both of them, and by combining both of them, you will reduce your energy. And this is a real concept. So they are working on that. And the things that was discussed, and there was a good exchange between the two communities, is in order to reduce the cost. Because now if you have fibers of 1.4 millimeter, and you need one silicon PM for each fiber, then it makes a lot of fibers and a lot of especially silicon PM, and this is expensive. So maybe we can reduce the cost by grouping several fibers to be read out in one silicon PM. And he did this study and to show that still we can distinguish between the photoelectrons, but okay, you have some the structure is not as good, the separation, but still it's good. So it should be followed and to see in the future what we can do. And he showed also that with this kind of prototype, you don't only study the efficiency or the energy, but you also can use it in order to check that the Xeon models are correct, and at least they are well reproduced by this prototype. So in the future, you need not to be a very huge one, because you can use the information from the simulation to improve and fine-tune your detector. Then Roberto gave us a nice talk about the simulation to confirm that and to see how we can use this simulation in order to find the right detector for the future, for the one we propose for CPC. And he did it for instance, here to see this famous ratio between the hadronic part and electronic part for proton in the Cherenkov part and in the scintillator part, okay? And then, this is interesting, he did it for lead and for copper. I think that I didn't mention here. This was for copper, okay? The one that, for instance, John was defending. But lead also could be a very nice solution. And Roberto showed us that even it's maybe better than the copper selection, because you can see here when you go for jet resolution and discriminate between W and Z, maybe the lead could do a better job. Of course, we have other consequences. I mean, please, I mean, when you see this kind of slide, be careful. You go to the talk of both of them and you compare, because you have additional things. It's not necessary only for this slide, because you have, I mean, for instance, it may be heavier, so we have other surfaces, etc. So we have to keep this all in mind before to make the selection, but at least we have the tools to be able to study, and this is interesting. And also he told us that the CPC colleagues in China are now, they included completely the simulation of the concept of dual readout in the CPC. So in the near future, we will see really full studies on the physics level. Now, there were two talks from the Calais collaboration. One talk was given by Vincent Boudry from LLR, who insisted essentially on the silicon tungsten, and this silicon tungsten, they were pioneers in proposing this, and he described to us how this is this conception and how the detectors will be built in order to take into account the advantage of the resolution and the energy measurement, okay? And he gave us the flavor of what we expect for the final ILD that is proposed for ILC, the ILD concept. And you see the number of channels, the number of ASICs, and what is was done right now. And you see we are trying to come closer step by the demonstration. You need not, but at least we need to have a prototype, a full prototype. By the way, there was a physics prototype that was produced, and the results were excellent. But now we want to have to demonstrate that we have a technological prototype, the same that the ones that we are going to use for ILC or for CPC. Okay, and they went really further, and this is maybe pictures that show you that they were able to produce a small prototype with 7 layers. Okay, I think about 20 by 20 centimeter. And they went to DAISY and tested not only with the electron, free electron, but in the magnetic field. And they obtained very nice results. And you can see they were surprised to have this ratio. I mean, this signal over noise, which is, was obtained, where is it? Should be somewhere. It's about 20, okay? I mean, you can read it over there. It's 20, which is really excellent, okay? And of course, they still work in order to have more, I mean, better uniformity, but it's the second step work, and also to solve the problem with some ASICs, with some data channels. Then the second talk from the Calais collaboration was about hadronic calorimeters. So some of them are common with the activities in China. And just to remind you that we have essentially in Calais 2 detectors, 2 calorimeters. One is based on the scintillator analog readout, okay? And there was a physics prototype that was built. You have a picture here about the size of the tiles that were used for 1 layer, okay? There were 38 layers, and this was read by the same electronics that we presented previously, which is Spiroc from Omega. And the results that were obtained, but I mean, just to be fair with myself, because these are our competitors, this prototype was done with the electronics outside the detector. It was not embedded. So right now, they are taking data with a new prototype where we have this 3 times 3 squared centimeter everywhere with a large one. So we are waiting to see if these nice results that were obtained are confirmed with this technological prototype, where you have all the problems with heating, whatever, all this. But I'm quite sure that they will obtain very nice results. Okay? And then the second one that was presented is this is the Ashka that was developed also within Calais, but this is a technological prototype. And we are talking about technological that we have embedded electronics, we have very few number of cables and coming out, so all this idea concerning the compactness is taken into account. And the results that were obtained are presented here, and it's interesting to see that, for instance, people were proposing in the past a binary readout, but if you go with a semi-digital readout, you improve at high energy resolution. So this is interesting also, and other people are following. And just one word about the granularity, which is very interesting, that you can use this granularity, and I can show you here, to select the track segments with your hadronic shower. So you can use your hadronic shower in order to control your detector in situ. But you can use them as well in order to connect, for instance, and this for PFA is very important, to connect this contribution and associate them to the same charged particle, for instance, okay? So this is very important. Now, the other talk that was given by Ivanka about the luminometer proposed for CEPC, and this is a common work with the colleagues from IHIP and from China. And she told us that this is very important, small device, but very, very precious and important, because for all what you do for physics measurement, you need to have a good idea about the luminosity, right? And for this, there is two proposals for this kind of detectors. Either the BGO scintillating crystal, okay? But this has, okay, it's very good, but has some disadvantages. Among others, the relatively low light output, but also the cost. And the second one, the one which is really favored, is to use, as for the ECAL proposed for CEPC and ILC, is to use the silicon tungsten. Of course, it was not the same segmentation, but this is very interesting. And for both detectors proposed, it could be supplemented by a layer of a tracker to discriminate between gamma and electron, whatever. So this work was presented, but which was very interesting in the presentation of Ivanka, that she tried with the colleagues to see what are the important elements for this kind of detector, and especially the measurement for the future. And you can see, and we were all looking carefully about this, that in order to achieve very nice resolution, 10 to the minus 4, you need to know very, very well the inner radius of your luminometer. But in addition, you need to know very well the energy of your beam. And according to her, it was maybe very, very difficult to achieve this resolution with the energy beam. But I remember that the presentation and the idea of Janos are to use this, the symmetry and the angle to maybe find the energy with good precision. So people, I think, should start to look carefully how to collect this information together in order to produce this nice precision required for the future. Now, there were other talks, and the first talk was about this development of ASICs, front-end electronics for calorimeters. And the talk given by Stefan from Callier from Omega was very nice. And really, if I can, people who are interested by microelectronics, they are not experts, but they need to know what it is, what are the problems, the challenges. I would recommend you to read this presentation. It's about 90 pages, but fully documented. And you have all the information you need, okay? And Stefan told us all the ASICs that were developed for the different kind of calorimeters proposed for CEPC and for ILC. And he added that it's not only for the E plus, E minus detectors, they are working on the P detectors. For instance, there's the activities of CMS with the HGCAL. They are proposing this very nice ASIC, which is high granularity HCAL for the HCAL. And you see that in a couple of years, they developed 4 series of that to cope with the request from CMS. And this is very important development, and I will let you know why, because we invited David Barney from CERN to tell us about the challenges they faced with this high granularity ECAL in the periworld region, which we call HGCAL. And he showed us this project and what we need to replace this very forward region of the ECAL that could not continue in the high luminosity because of the radiation rate and the degradation of the scintillators. And he told us that this is really very important. And if you want to propose a solution, you have really to have something which is radiation tolerant, okay? And the rate is very, very important. And in addition, you need timing for pileup mitigation, timing for many other things. Okay, he showed us where the concept, and where they are, they did some test beam, and they obtained very nice results. You can see here. Of course, it's not as good as the one with ECAL, but it's not the same conditions here and not the same requirement. And you can see that they see the MIPS, okay, and they are happy. And they produced, you can see, I don't remember what is the number of flares, but they did it in a time record, indeed. Okay. And he told us that timing is very important. And from the electronics point of view, you need really to reach at the level of 50 picoseconds. Okay? And if you use timing, you can see how you can clean what you see in your detector. Okay? Now, I will finish with something that came at the end. It was kind of invited talks. It was not in the heart of our calorimetry, but I think it's worth trying to have a look on it and see that it was, Gary presented to us a very nice device that could be used for silicon PM readout. It's about the idea how to detect the neutrino of high energy interaction, looking for radio frequency Cherenkov, as it is the article in 1960. And this is the concept of the detector proposed. I will not go into details. I'm not a real expert, but the idea is to measure the signal pulse and the time arrival in a very precise way by looking at the waveform. Okay, you can see here. And have very nice achievement, a kind of oscilloscope, very precise oscilloscope on a chip with acceptable price and also with power consumption is very, very good. And they did some work indeed to reach this, and you can see they obtained a resolution of a few picoseconds. Now, let me finish with the last talk that was given remotely by Martin Alexa, and you know that CERN asked to prepare the future, R&D future, and Martin was of the two people who were asked to prepare things for calorimetry. So he gave us a review about the activities of this group and where they are going to invest in the future, at least the ideas proposed. And one of the things that he told us is about FCC-HH, among others, because they are also working on a click and also LHCb. But since it is the most important topic for the CPC and SPPC in the future, I will let you read this carefully. Essentially, they want to work on the argon liquid and to improve the granularity and the electronics and other aspects, but not all. And they want also, and they are asking to collaborate with other communities on these different aspects. And I think the CPC could be interested to collaborate with the CERN group. Okay, I hope I was not too lengthy. So first of all, I would like to, in the name of my colleagues, the conveners, Roberto, Imo, and Jenbei, to thank the people, the speakers. It was very nice talks and a very good quality. And also thank you for your attention. Thank you very
much. Any comments?
I'd like to make a brief comment regarding the power consumption of the various type of calorimeters. I'd like to point out that with the dual readout solution, you can have all of the electronics in the back. And that's a big advantage because in principle you can come in with a 10-inch pipe of refrigerating liquid and cool everything you want. Well, instead, if you have the electronics distributed all over the volume of the calorimeter, that makes it much harder.
Yeah, I understand. I think you have some advantages, okay? But let me tell you that for the other solutions, you have also, for the other technology, you have solutions. For instance, in the HCAL of CMS, which is a huge amount of heating, etc., they found a solution, okay? I mean, you have pipes within the, and they have active cooling. Of course, if you...
No, I'm not saying that there are no solutions for the other option.
Well,
I'm just saying that it's easier.
Yeah, I agree with you, but I would like to wait until a big prototype to see the output.
Okay, so let's thank all the speakers again.